Okay, so to begin with this chapter, chapter 7, we're going to be focusing on exponents. Now, in reality, chapter 7, 8, and 9 could really have been combined all as one giant chapter. Now, obviously that wouldn't make sense because that'd be a lot to cover in one big chapter, but what I'm getting at is the fact that chapter 7, 8, and 9, there's a lot of overlap between these chapters. So you want to make sure that you're understanding this material. So if you have questions, you want to make sure that you're either rewatching these videos or you're making appointments to see me so you can get your questions answered. Because you don't want to get to the point where you start to think that, oh, I'll wait till next chapter to figure this out, because next chapter is going to build off of what we're learning about this chapter. So previous chapters we've talked about, each chapter was kind of a fresh beginning, where with this chapter we're going to be starting with this chapter, there's going to be a lot of overlap. Now the nice thing is this first section starts out with some basic concepts to make sure that you understand some basic things with exponents. And first off, that's just understanding what an exponent is. So an exponent, remember, is the number that's in the air. But this is something new. So this is something that you want to make sure that you get down in your notes, especially understanding this term will be especially helpful when we get to chapter 9 and we start talking about logarithms. And that's this idea that if the exponent's the part that's up in the air, the part that's sitting on the ground, we call that the base. And this as a whole we refer to as a power. Now this next sentence here should be maybe common sense or something that you're already familiar with, and that's this repeated multiplication. And the repeated multiplication definition of a power tells us that if I have x times x times x times x times x times x, that's the same as x to the sixth. Or going backwards, it's important to understand that if you have x to the sixth, that's the same as x being multiplied times itself 6 times. And that'll be important to remember when we talk about some different rules and properties in the next lesson. Now this whole idea with this repeated multiplication, one application of this is dealing with a probability. Now suppose a quiz has 10 multiple choice questions with 4 choices each. So if that's the case, each question has a probability of 1 in 4, or 0.25, to get the question correct. Well, since there are 10 questions, the probability can be found by doing this. Well, every single question has a 1 in 4 chance of getting it right. 2, 3, 4, 5, 6, 7, 8, 9, 10. So if each question has a probability of 1 in 4, or 0.25, obviously I don't want to sit here and multiply all these together or even list these all out. So a faster way to do this is to use that repeated multiplication definition. And that's saying that if you have a 1 in 4 chance of getting one question correct, that would be if you're guessing, then you would have, and if there's 10 questions total, it would be a 1 in 4 to the 10th power, or you could write it as 0.25 to the 10th power. Leaving it at a fraction, though, we get 1 over, it's 1,048,576. So you have a little over a 1 in 1 million chance if you guessed on that multiple choice question test of getting all of them correct. Or as a decimal, if you did 0.25 to the 10th power, it's going to be a big decimal. In fact, your calculator might even put it in scientific notation, but it would be 0.000000, so 6 zeros, 954. That's what the probability would be as a decimal. Now let's look at graphing probabilities. So let's say, suppose the probability of an event happening is p. So if you don't have my notes, you want to write this example down. This is the kind of example that you'll be seeing in your assignment. So we're going to come up with an equation here to represent the situation, and then we're going to graph it. So first off, when you see this phrase, find a formula for A, that means that we want it in the form A equals something. And in terms of P, means that the variables that we're going to be using is going to be P on the other side of the equal sign. Now in the example that we looked at a minute ago, we knew that there's a 1 in 4 chance of us getting each question correct. Well, this is leaving it up to argument as far as P could be any probability, not just a 1 in 4 chance. So we're just going to use P to represent the probability of the event happening. We want to figure out what the graph would look like if we want to figure out the probability of it happening 4 times in a row, so it'd be to the 4th power. So my independent variable in this case is P. My dependent variable is A, the total amount. So I'm going to set up, well, first off, before we do that, here's a little note about probabilities, and that's the fact that probabilities are always between 0 and 1. Okay, that's important to remember. So probability of 0 means that it's impossible to happen, and there's no such thing as a negative probability. And a probability of 1 means that it's guaranteed to happen. There's no way for it to not happen. So let's look at some different probabilities for this particular event. So I'm going to put in some numbers like 0. I'm just going to base it on this graph. 0, 0.2, 0.4, 0.6, 0.8, and 1 whole. So again, a probability of 0 means that it's impossible of happening 1 time, so that means it's going to be impossible to happen at all 4 times in a row. 0.2 means that the probability of the event happening just 1 time would be 0.2, or a 20% chance if you put it in terms of percents. We want to figure out what the probability of it happening 4 times in a row would be. So I would take 0.2 to the 4th power. Well, 0.2 to the 4th power is 0.0016. Okay, so that's how we got that. So let's stop and talk about that for a second. So that means that if a probability of event happening is just 1 time is 0.2, the probability of it happening 4 times in a row is less than 1%, because if I change this to a decimal, it would be 0.16%. So it's a very slim chance of it happening 4 times in a row. If the probability of an event happening 1 time is 0.4, the probability of it happening 4 times in a row would be 0.4 to the 4th power, which is 0.0256. So 0.4 is the same as 40%, so that's twice as good. And here but yet happening 4 times in a row is still less than 3% chance of that happening. Let's say if we do an event that's better than a 50% chance, of 0.6 probability, well, the probability of that happening 4 times in a row would be 0.1296. So still less than a 13% chance of happening, not very likely. Now the probability of an event happening with 0.8, well, that's a pretty high probability. However, 0.8 to the 4th power is still only 0.4096, or about 41% chance of happening. So even though it's a real high likelihood of happening 1 time, the chances of it happening 4 times in a row is still less than 50%. And lastly here, if we have a probability of 1, that means it's always going to happen no matter what. Well, then it's always going to happen 4 times in a row, because 1 to the 4th power would be 1. So now when we go to graph these, let's look to see what this graph is going to look like. So 0, 0 would be here. 0.2 and 0.0016, well, that's hardly off of 0. And 0.4 and 0.0256, well, that's going to be a little higher there. 0.6 and 0.1, well, 0.2 is here, so 0.1 would be halfway, so 0.13 would be a little over halfway. And 0.8 and 0.4, that's pretty much just 0.4 there. And then 1 and 1 would be up here. So when we connect these, a note about these types of graphs is, like I mentioned earlier, there's not going to be any arrows because there's not going to be a percent larger than 1 or less than 0. So that's what your graph would look like for this particular scenario, meaning we're going to look at, this is the probability of event happening 4 times in a row. Okay, so there's some terms we need to be familiar with, dealing with different probabilities, or different, I'm sorry, not even probabilities, dealing with different exponents. So you want to make sure you get these different terms written down, because sometimes they're going to ask you, they're not going to give you an equation, they're just going to ask you to graph the cubing function. Well, if you don't know what the cubing function is, you're not going to even know where to start. So we're going to skip x to the nth for right now. But let's look at the first one here. X to the 1st power is what we call the identity function. Now let's talk about this term identity. Identity just means that in math, it's what would we do to a number for it to stay the same. For example, the identity property of addition is that we would add 0, because 5 plus 0, it would stay as 5. The identity property for multiplication is that we'd multiply that number times 1, so 5 times 1 would stay 5. The identity property here with exponents is that our exponent would be to the first power, because 5 to the first power would be 1. So that's why we call this the identity function, because the numbers we put in there for x stay the same. X squared, we call that, well, if it's squared, we'll call that the squaring function. Oops. So if that's the squaring function, if I have something raised to the third power, we would call that then the cubing function. Now, important thing to know is that any exponent greater than 3 do not have special names. So anything beyond that we just call nth power functions. So anything raised to the 7th power, we just call that the 7th power function. So everything that we're going to be looking at least in this lesson, are what we would call nth power functions. So they'll always have either an odd power function, even power functions. All of these would be in this category of nth power functions. So speaking of odd power functions and even power functions, that's what we're going to look at here. We're going to compare two graphs. This first one is going to be for an odd power function. And the next one is going to be for, I'm going to have to write it up here, this is going to be for an even power function. Because within these two different types of functions, whether even power function and odd power function, all odd power functions share some similarities, and all even power functions share some similarities. However, going between odd and even power functions, there's very few things that they have in common. So let's look at these graphs of, first off, the cubing function. Recall that's y equals x cubed. So to graph this, we're just going to start out with an xy table and go to our popular numbers, -2, -1, 0, 1, and 2. So if I put -2 in there for x and cube it, that's going to give me -8. Remember, we're cubing it, not multiplying it times 3, so it's not -6. It's -2 times itself 3 times, which is -8. -1 cubed is still -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. So when I go to graph this, -2, -8 would be down here. -1, -1. 0, 0, 1, 1, 2, 8. So here's your graph. So if we have odd power functions, are always going to be in this quadrant. If we look at in these two quadrants, the quadrants are in are quadrants 1 and 3. So again, all odd power functions are going to be in quadrants 1 and 3. And all odd power functions have these 3 points in common, 0, 0, 1, 1, and -1, -1. Okay, so now let's look at what the domain and range of this would be. The domain for this would be all real numbers. And the range would be all real numbers. The reason why is because looking back at the original equation, I could put anything I want in there for x. So if that's the case, that means that my domain would be all real numbers. Looking at the graph, my graph goes infinitely up, goes infinitely down, so my range would also be all real numbers. So again, this is true for all odd power functions. The only one that's unique is y equals x to the first power. Y equals x to the first power would look like this. Otherwise, they're all going to go through, but if you notice, it still goes through these 3 points, 0, 0, -1, -1, and 1, 1. But all odd power functions, other than y equals x, is going to be this little zigzag line. Now let's talk about even power functions. Y equals x to the fourth. Again, let's set up an xy table. Negative 2 to the fourth power is a positive 16. Again, you're raising it to the fourth power, meaning multiplying it times itself 4 times. Negative 1 to the fourth power is a positive 1. 0 to the fourth power is 0. 1 to the fourth power is 1. And 2 to the fourth power is 16. Now here I'm going to count by 2's. So when I go to graph this, and I'll count by 1's on the x-axis. When I go to graph this, negative 2, positive 16 would be up here. Negative 1, positive 1. 0, 0, 1, 1, and 2, 16. So again, there's some similarities here with all even power functions. They're in quadrants 1 and 2. All even power functions have a domain of all real numbers and a range that's greater than or equal to 0. For y. Okay, so again, this is true for all even power functions. Now this is not technically called a parabola. A parabola is reserved for y equals x squared. So we would just call this the graph of an even power function, but it does have some similarities to a parabola. They do look very similar, but they are not exactly the same. But again, all even power functions will always be in quadrants 1 and 2. All odd power functions are in quadrants 1 and 3. That'll be important to note for some of the questions that will be in your assignment. So with that, good luck on your homework.